Hi everyone, let's go ahead and get started on your notes. If you're in first, second, or third period, then you know I'm not at the school building today, and I am expecting you to have your notes completed just like you would if I were there and to be working on that practice. And I know that y'all are going to do great. So let's go ahead and jump in. So we are going to be talking about the law of conservation of matter, types of chemical reactions, and indicators that a chemical reaction is happening. And so when there is a chemical change or a chemical reaction, and those things are the same, okay, when those things occur, there are indicators or signs that a chemical reaction or chemical change has happened. Okay, and so the six indicators are precipitate, color change, temperature change, gas production, water production, or water as a product, and odor change. So change in smell. So one thing that I would like to go through, and I'm going to go through and we're going to explain all six, but I wanted to have them all out there first. So a precipitate, that's just a solid, okay? So for example, if I have a liquid and I add it to another liquid chemical and it produces a liquid and a solid, okay, that new solid on the product side would be considered a precipitate, okay? So that's kind of what we're looking at there. So you want to pay attention to your states of matter. Now, for a color change and for temperature change, the key thing for both of these is that they are unexpected, okay? They are unexpected. So, for example, if my two liquids that I mix together in my first example, let's say liquid 1 is clear and liquid 2 is also clear, if I combine them and my solid is now all of a sudden yellow, that would be really unexpected. Whereas if I mix orange and red, yellow and red food coloring and I get something orange, that's not unexpected. Or for temperature change, boiling water is not an example of a chemical reaction, because one, the water remains water, and two, that is not an unexpected temperature change. In order to boil water, you had to put it on your stove. You purposely added heat there, and so you knew the temperature was going to change. Gas production. An example of this is producing any sort of gas. So if we look at, for example, a photosynthesis, C6H12O6, which is glucose or sugar, combines with oxygen, and when it does, oops, I put two arrows there. Okay, it combines with oxygen, and when it does, it produces carbon dioxide gas and water. Okay, now here's the thing. The fact that you have a gas on the as a product, that means that you're going to see a couple different things. You might see bubbling. Okay, so bubbles. You might see fizzing is another thing. So like when we add baking soda and vinegar, okay, you might also see smoke. Those are all three things that are indicators that you made a gas. And we see that in this example, there's water, H2O, on the product side, and that's our fifth indicator. Now, an example of an odor change would be rotten eggs or spoiled milk. Okay, whenever you have that really bad smell there, and you know it was not there before, that change in odor can let you know that a chemical change has happened and something new has been created. And in the case of spoiled milk, that new thing is going to be really gross, and you should really toss out that milk. So these are the 6 indicators of a chemical reaction. And you saw a lot of these in the reaction in a bag lab that we did in class last week. Or if you're one of the virtual students, you saw it in the online lab that you did. So now we're going to move on to the law of conservation of matter. Okay, the law of conservation of matter is anything that has mass, which remember is our amount of matter. You don't have to write this part down, but I just want to have it there as a reminder. So anything that has mass and volume. And remember, volume is the size or the amount of space it takes up. Okay, and it's made up of tiny particles called atoms. The law of conservation of matter says that matter cannot be created or destroyed. This is hopefully something that you remember from middle school. Okay, the law of conservation of matter says that matter, which are made up of those atoms, cannot be created or destroyed. It can only be rearranged or changed. Okay, so we can change what it physically looks like, or we can rearrange those bonds, but this means that atoms are not created or destroyed during a chemical reaction. That means that there must be the same number of atoms on each side of the reaction. Okay, you can't magically have extra oxygen atoms or create, have atoms just disappear. Okay, they all go somewhere. And so when we look at what that looks like, there are a couple of ways that you might be asked about the law of conservation of matter and that we want to observe. So we're going to create a particle diagram that's about this chemical reaction here. Okay, so we've got our chemical formulas or the symbols, and then we have them written out as their names. So we're going to create a particle diagram, or for this particle diagram. So we have calcium, we have chlorine, we have sodium, sulfur, oxygen. Those are our chemicals. So we're going to create some keys. So I'm going to make calcium pink, chlorine blue, sodium purple, sulfur is this dark blue, and oxygen is green. Now you should have color pencils at your desk, so make sure that you pull those out and we can create colors. You obviously don't have to have the exact same ones that I do, but you want to have some of them, or just 5 different ones. Now remember, there's no number here in front as a coefficient, so that means we have just 1 molecule of calcium chloride, we have 1 molecule of sodium sulfate, 1 molecule of calcium sulfate, and we have 2 molecules of NaCl. So remember, that coefficient tells us the number of molecules, and our subscripts, or these smaller numbers, tell us the number of atoms that are in that molecule. Okay, and so remember, chemists are lazy, so there's nothing here for calcium, so it's just 1. So I'm going to have my 1 calcium atom combining with 2 chlorine atoms. So I'm just going to draw it this way. Okay, so we've got calcium chloride plus 1 sodium sulfate. So we've got sodium. So I'm actually going to draw my sodium atom first with my 4 oxygen atoms around it, because we're going to get into this more later, but it's considered a polyatomic ion. That sulfur and 4 oxygens, they like to stick together. And then I'm going to draw my sodiums kind of like that. So we have these chemicals that are combining, and they're liquid, so they're kind of moving around slowly. I'm not going to draw their movement per se, but we see that it's combining with a calcium sulfate. So again, I'm going to draw my sulfate, or my blue with 4 oxygens here, and it's only got 1 calcium atom in it. So we have our red molecule, and it's combining with 2 sodium chlorides. So that's a purple with a pale blue and another purple with pale blue. Now, the thing that we want to notice about this is when we count things before and after. So for example, if you look at questions 1, 2, and 3 about this particle diagram, the first thing that it asks you is how many calcium atoms are there before and after. So if we look at calcium, which is red, we can see that there's 1 calcium atom here and 1 here. So we have 1 before and after. Okay, and it says do the other elements follow the same pattern? Well, if we look at our chlorines, I have 1, 2 light blue circles on the left side and 2 on the right side. If I look at my purple ones, I have 2 on the left side and 2 on the left side. I have 1 dark blue and 4 oxygens on both sides. So yes, they're all the same on both sides, or before and after the reaction or change. Okay, so they're the same before and after. So the amount you have to have must be equal. Now, when we think about was this a physical or chemical change and why, notice here my calcium is bonded to chlorines, okay? But on the product side, my chlorines are bonded to sodium. So this means from here to here, there were new bonds created. You had to break the bond between the pale blue and the red in order to get pale blue and purple together. So new bonds means a chemical change. So this is the chemical change. And it's because of new bonds. And I didn't leave enough space for me to write that there. But when we think about this, that also means that all of those atoms, if you look on your periodic table, okay, for example, if you look at oxygen, which is number 6 on the periodic table, no, excuse me, it's number 8 on the periodic table, at the very bottom, it has the number 16.00. That's the mass, okay? And so that means every oxygen, every hydrogen, every calcium and chlorine and sodium, they all have a certain amount of mass. And if the numbers of them are the same, that means that the total mass of the reactants, okay, or your ingredients, remains equal to the total mass of your products. So if you look at your mass before the reaction and your mass after the reaction, it should be the same, okay, always. Now, one thing to keep in mind is if you do a reaction, like let's say we mix baking soda and vinegar, okay, and then all of a sudden you've got smoke or bubbles fizzing out of your container. If you don't have a lid to keep all of that trapped in there, smoke, it weighs things. So we got to keep that trapped in there so that it stays the same. So we've talked about indicators. We've talked about the law of conservation of matter and mass. And now we're going to get to the last part, which is types of chemical reactions. And when we're done with this, you'll then have practice problems that you can work on to really see how it might show up. Okay, and these practice problems are very important. So the first thing is that when we look at types, okay, there are 5 main types that we're going to learn about, and I've given them all nicknames. So the first one is synthesis, and synthesis gets the nickname of marriage. Okay, so when we're describing what a synthesis reaction is, this is when you have 2 chemicals, okay, or 2 reactants. Okay, 2 chemicals combine to create one product. Okay, so we have 2 reactants, but only 1 product. So this, for example, would be like if you have chemical A plus chemical B, and now A and B are combined. Or a real life example of that would be hydrogen gas plus oxygen gas creates water, okay? And it happens in a 2:1:2 ratio. But you have two reactants, okay? We've got oxygen and we have hydrogen, and then they combine to create one product, H2O. Now, decomposition is the opposite of synthesis, and that means its nickname is the opposite of marriage. It's called a divorce. This is when you have one reactant or one chemical, okay, that breaks down into two. Okay, so when we talk about decomposition, it means to break down. So, two products. So this is just the reverse. So this is if you have chemical AB and it breaks down into A plus B. This could also be in real life if you have magnesium oxide. It can be split apart into magnesium plus oxygen. And so this is decomposition. Now, single replacement reaction, okay? A single replacement reaction gets the nickname the homewrecker. Now, the reason why it gets the nickname homewrecker is because you're going to have one compound. So let's say we have AB. So it's one compound, okay? But it's also an element. So you have one compound and element. So we have AB, and then we have just C, all by itself. Okay, and I'm going to make that smaller. AB plus C. So we have a compound, which I'm going to highlight in green. And then we've got an element, okay? And what happens is that new element, element C, that's the homewrecker, okay? Because when you have a compound and an element, they combine and they swap. So they combine and trade places. Okay, so for example, if C and A are similar, then all of a sudden C is with B and A is by itself. So your indicator really is that one element and compound combine to create a new element and compound. But notice that you still have a compound and an element on both sides. So our new compound is CB and our new element is A. Okay? But it's always a compound plus a single element on both sides. Now, a double replacement reaction is called wife swap. I don't know if you've ever heard of this show on MTV, which kind of makes me feel old, but it was called Wife Swap. And it was basically these families where the wives would trade houses for a week, and the studio TV people would record the drama that would ensue. And so this is when, okay, so you have two compounds that trade metals. Okay, you're going to have two compounds that trade metals, or we're going to learn later that they're also called cations. Okay, so for example, if you have chemicals AB plus CD, what happens is that A and C trade places. And so now you're stuck with CB plus AD. Okay, so an example of this would be the experiment that I apparently did not describe at the beginning of the video. So there's an experiment that involves potassium nitrate and lead iodide, and it creates lead nitrate and potassium iodide, and this chemical reaction, you can see, has two compounds on both sides. They're just slightly different from each other. And then the last but not least is combustion. And combustion is called baby mama drama. Now, you might be saying, Ms. Nichols, why is this called baby mama drama? Well, for the longest time, I didn't know what to give a nickname for this. But one of my students a few years ago decided this is what it should be called because combustion reactions are the reactions that go boom and they blow up in your face. And if you're using the words baby mama drama and you're not joking, then something has probably gone wrong and things have blown up a little bit. So a combustion reaction is a reaction with a hydrocarbon and oxygen. So hydrocarbon reacts with oxygen to produce carbon dioxide and water. Okay, so in this type of reaction, you would have, for example, CYH or CXHY, and it combines with oxygen gas, O2, and it will always form carbon dioxide gas plus water. This is all that it does. So, for example, photosynthesis, right, is where we take glucose and it combines with oxygen. Don't know why I put an arrow there instead of a plus sign. Combines with oxygen to create carbon dioxide plus water. Or, well, I guess this is cellular respiration, not photosynthesis. But the point being is that it always, always, always has carbon dioxide and water as its products. Okay? And it also will only have C, H, and O in it. It will only have carbon, hydrogen, and oxygen in the reaction. And so now if you need to restart the video, if you missed a part, or you need to pause, please go ahead and do so. But now that you've got your notes, what I want you to do is apply your notes to these practice problems. So here on this line, you're going to put what type of chemical reaction it is. Okay, if you want to maybe get a head start or do a little bonus, see if you can figure out what coefficient you would need to put in each spot to make it balanced. So for example, if you notice I have 2 bromines on the left but only 1 on the right, so we would kind of have to have 2 potassium bromides, 2 potassiums there, and then 1 and 1 to be balanced. Now obviously I didn't teach you that in there. We're going to get to that later in the year, but if you just want to give it a go and make an attempt, then that would be great. And then in this part, okay, you're going to answer the questions about each experiment. Pay attention to if you have your reactants and your products, remember that according to the law of conservation of matter, the reactants mass must be equal to your products. And so you can set this up as kind of a reaction. So for example, in number 9, if you have this, you could almost turn it into a math equation. Your question mark can be X plus 16.0 grams equals 40.3 grams, because we know the left and the right side have to be equal to one another. So now you can solve for X. Okay, don't forget that if you're moving a number to the other side of the equal sign, you do the opposite of its math operation. Okay, and so you've got some different experiments and things to practice. And you're going to want to make sure that you complete it so that we can go over it together in class. And good luck, and I will see you next time.